Welcome to this Ray Optics quick revision session. This crucial topic forms the backbone for understanding mirrors, lenses, and key phenomena like reflection and refraction. Let's dive deep into concepts to simplify your JEE preparation. Ray optics plays a vital role in your JEE physics exams. Through this session, we'll simplify the fundamental principles, important formulas, and problem-solving techniques to help you ace this chapter. Get ready for a focused and effective revision. Reflection obeys two simple yet important laws. First, the angle of incidence equals the angle of reflection. Second, the incident ray, reflected ray, and normal all lie on the same plane. These are foundational, so keep them clear for solving problems. Reflection can be regular or diffused. Regular reflection occurs on smooth surfaces like mirrors, producing clear images. Diffused reflection happens on rough surfaces, leading to scattered light and no clear image. Remember this distinction for exam questions. Plane mirrors form virtual, upright, and same-sized images. A key point: the object's distance equals the image's distance from the mirror. When two mirrors are angled, use the formula n is equal to 360 degree theta 1 to calculate the number of images formed. Spherical mirrors, concave or convex, have specific image-forming rules. Use the mirror formula 1/f is equal to 1/v plus 1/u and magnification formula m is equal to vu to determine image properties like size and orientation. Practice these for assurance in problem solving. Mirrors have real-world uses. Plane mirrors are in periscopes or kaleidoscopes, concave mirrors in headlights, and convex mirrors in vehicle rearview mirrors. Understanding applications sharpens both exams and real-life comprehension. Refraction bends light at interfaces due to speed variations across different media. Study Snell's law, n1 sin1 is equal to n2 sin2. Key concepts include refractive index and critical angle, vital for numerical problems and real-life examples like TIR. In TIR, light reflects entirely within the denser medium when the incidence angle exceeds the critical angle. TIR is utilized in optical fibers and diamond brilliance. This is an essential application-oriented topic for JEE. Apparent depth arises from refraction, making submerged objects appear shallow. Use the formula apparent depth is equal to real depth n to solve questions. Consider examples like coins raised visually in water. Lenses, convex or concave, direct light differently. Convex lenses converge rays, while concave lenses diverge them. Remember their practical uses: convex lenses in projectors and concave lenses for myopia correction. The lens formula, 1/f is equal to 1/v, 1/u connects object distance, image distance, and focal length. Power, P is equal to 100/f, in diopters, reflects a lens's ability to bend light. Higher power lenses are pivotal in optical design. Lenses have diverse uses. Convex lenses magnify in microscopes, while concave lenses correct myopia and create diminished images for glasses. Mastering lens formulas ensures readiness for application-based questions. Learn about key optical instruments, the eye, telescope, and microscope. These devices apply reflection and refraction principles in daily utilities and experiments. A strong grasp of their working is vital for JEE success. Our eye is a natural convex lens. Its accommodation adjusts the focal length to focus on objects at varying distances. This adaptability allows clear vision from near to far points, a concept directly tied to lens use in optics. Defective visions like myopia and hypermetropia are corrected using concave or convex lenses respectively. For presbyopia, bifocal lenses integrate both corrections. Knowledge of these real-world issues ties physics to daily life applications. The simple microscope magnifies using a convex lens, forming a virtual, erect, magnified image. Maximizing power requires shorter focal lengths, simplifying its application in biological studies and lab experiments. A compound microscope uses two lenses, an objective lens for magnified real images and an eyepiece for further magnification. Its combined power enables viewing microscopic details critical in research and diagnostics. Telescopes enhance distant viewing via refraction or reflection. Refracting telescopes use lenses, while reflecting ones use mirrors. Reflecting designs minimize chromatic aberration, essential for exploring astronomy effectively. Dispersion splits white light into colors, forming rainbows, while scattering explains why skies appear blue or sunsets red. These phenomena demonstrate fascinating real-life applications of refraction principles. Understand them to connect physics with nature.